All right, let's do the sample final. So we have Not So Fashionable has 5 shirts and 3 pairs of pants. So if I go 5 shirts in my tree diagram, oops, and 3 pairs of pants, and none of these are a case where we'd wear more than one of them, and none of these are a case where we could go without them. So we're not saying wear a shirt or not wear a shirt, wear a pants and not wear a pants on each of these different pants and shirts. So it's just this regular one here. And now we need to label here. 3 shirts are striped and 2 are solid. So 5 shirts, so striped, S-T-S-T, and S-T, S-O, and S-O. And the solids are green or yellow, and the striped are pink or green or blue. And the pants are yellow, pink, or blue. 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 And yellow, pink, or blue. Draw a tree diagram. Got it. How many outfits does he have to choose from? Well, there's 5 times 3, which makes it 15. And then, what is the probability the outfit is pants of the outfit is pants of the same color? Pants and shirt, it should say. That's not worded well. So pink, pink, there's 1, they're both the same. Green, no. Blue, blue, there's 1. Green, none. And yellow, yellow. So there's 3 out of the 15, or 1/5. Okay, what's the probability the outfit has green or yellow? Well, they're green ones. There's 6 greens, and have yellow in it. That's 1, 2, 3, 4, and all of those 3. So 4 plus 3 is 7. That's a total of 13. But I've noticed that I've counted some twice. The ones that were yellow and had green. There's 1 there and 1 there. So I've counted 2 twice. So I got to subtract 2 from the ones I've counted. So that's 13 minus 2, 11/15. Now you could have also done it by just counting, does it have green or yellow? That has yellow. That's 1. That's all 3 of these have green in them. So 1, 2, 3, 4, 5, and then we have 6, 7, 8, 9, and then 10 and 11, because all of these have yellow. And there's the 11. And E. What's the probability that there is no green in the outfit? So the green only happens in the shirts, and that's these 3 and these 3. So all the other outfits would not have them. So that's 6 that do. So 15 minus 6 is 9/15, which 3 goes in both of those, 3/5. All right, Number 2. Imagine we were trying to draw a random card from a deck of 52, and then we don't replace it, and we draw again. What's the probability of getting at least one ace? Well, this sounds like I only drew twice, so we can do it with twice because it says without replacing, and you draw again. So it sounds like it's only twice. I probably would put a 3 times or say how many for sure, but you draw again. So 2. So at least one ace means the only thing we don't want is no aces. So we do 1 minus the probability of not getting an ace. So that would be 1 minus the first draw, not getting an ace. Well, there's 48 cards that are not aces out of the 52, because there are 4 aces. And then if I don't replace, then there would be only 47 to choose from out of the 51. So I would pull out my calculator and see what that comes out to be. So if I do 48 divided by 52 times 47 divided by 51, I get 0.85. So I have 1 minus 0.85, which is 0.15. Okay, move some of that stuff out of the way here. So number 3, suppose you're tossing 2 fair dice, and we're supposed to draw a way to show the sample space, and I think that grid is probably the easiest. And there's 1, 2, 3, 4, 5, 6. That might be small for you to see in the video, but you're familiar with this enough that I hope you can do this without having to see it in the video. 1, 2, 3, 4, 5, 6. So there's A. Event of rolling a sum of 4. That'd be 3 and 1, 2 and 2, or 1 and 3. And that's A. And B is doubles, so that's this way. 4, 4, 5, 5, and 6, 6. So I put some more information on there, and then it says fill in the table. Well, there were 6 doubles, that's B, so I'm going to go to B and go to the totals. And the probability is 6 out of 36. And go back to A, there was 3 of them, so for all of A down here in the total, I'm going to put 3 out of 36. Now how many are in A and in B? And is one box, so that's an and. A and B, well there's 1 in both. So if there's 1 here and B's total is 6, means 5 B's are not, there are 5 doubles that are not in A, the sum of 5 or 4. 1, 2, 3, 4, 5. And there must be 2 here because 1 and 2 make 3. And that means that of the A's, 2 of them not in B. And of course this has to be 36 out of 36. So this has to be 30 here. And this has to be 33 here. And then that means 2 plus 18, 28 is 30. Or 5 plus 28 is 33. So there's the table filled in. Probability of not being a B. Well, B was the doubles. There's 6 of them of the 36. So that means there's 30 others that are not B. or 5/6 if you want to reduce it. A or B. Well, there's 3 in A and 6 in B, so that's 9, but I've counted 1 twice, so there's really only 8 out of 36, which is 4 goes into both of those, 2 ninths if I reduce it. E, A and B, well that's 1 out of 36. A given B. Well, if we know that we have B, that's only 6 of them, these 6, and how many of those are B? Oh, excuse me, if we're given B, yeah, B is the doubles. How many of those doubles are A? 1 of them. 1 out of the 6 that are B. Okay, that's page 1. Page 2. How many ways are there to select 4 students? Now, if you're just selecting 4 students, that would be combinations. But since we're going to order them in terms of president, vice president, secretary, and treasurer from a class of 30, that would be permutations. NPR. And the number we're selecting from is 30. And the number of positions that we are filling are 4. And so how many ways are there to do it? So on my calculator, I push 30, math, probability, NPR, pick 4, and arrange them. 6, 5, 7, 7, 2, 0. Which is 30 times 29 times 28 times 27 if you don't have NPR in your calculator. Because there's 30 choices for the president, and then there would be 29 choices for a person to be vice president, and 28 to be secretary, and 27 to be treasurer. Now, if I didn't say specific positions, just pick 4 people to represent, then I'd have to divide this by 4 factorial, and it'd be fewer ways to just pick 4 people. Okay, 5. Insurance company charges $180 a policy. So, the probability and the value. You should be used to multiplying this to get the expected value for just $100,000 policies. So I take 100,000 times 0.0002, and I get 20. And that's dollars, because units was dollars. And it's real important for you to understand what this means. The insurance company sells policies for a price. It then plans on putting some of this away in either in savings or investment to pay off the expected claims. For example, they expect to pay $100,000 in claims several times. And by taking the probability that a particular claim amount would happen, time how much the money is, they get what's called the amount that they need to save to pay for all $100,000 claims. And now if we do that for the other ones, we'll find out how much of each policy needs to be put aside for each of the values of the claims. So next one's 50,000 times 0.0008, and that's $40. And then on the $10,000 claims times 0.002, they're going to have to set aside $20. And of the $3,000 claims, they're going to have to set aside $12. So that's money that they're going to pay out on each policy holder They're going to bring in their $180 and they're going to pay out 20 and 40 and 20 and 12 to pay off all the claims. That's what the actuaries, the math people for the company, tell them that they need to have. The rest of that goes into paying off the company and profit and pay the wages and facilities and all the taxes and everything else they got to pay. So the first question, how much is paid out for claims of $100,000? Well, $20 a policy, but they had 600,000 policies, so we would take $20 times 600,000 and we get 112, let's see, that puts another zero, 12 million. That's a lot of money they're paying out in claims. But they're bringing in even more, we'll see here in a sec. Or not even more, but they're making money still. So they're going to pay out that much on that. Well, they're going to be paying out a bunch on all of these here. Now, before we do how much money the company makes or lose, let's figure out how much they're going to have to pay out and bring in on each policy. So they're going to have to pay 20 plus 40 plus 20, that's 80, $92. Out of every $180 they bring in will go to pay claims. So how much are they going to make per policy? Well, since the amount they're bringing in per policy is 180, it's more than the 92, so they're not going to have losses. They're going to have earnings of 100 minus the 92 they pay out, which is $88 per policy that they can use to pay for their expenses. So how much money did the company make or lose? Well, since the percentage probabilities were kind of low, we're going to have 88 times 600,000. $88 times $600,000, or 600,000 policies, and we get 88 times 600,000, and that's 52,800,000. Okay. Why is that? Oh yeah. So they are making out pretty well. They've got a lot of money here to be able to pay their agents and pay for buildings and whatever to cover them. And they can also put some extra away for savings in case there's a natural disaster that really hits their company hard. And their policyholders have a lot of claims. So that's the idea on that one. Now, one thing I might mention while I'm here is we could have done number one, or part A, differently here. If there's a 0.0002% chance of a policy needing 100,000, I can take the 600,000 policies times 0.0002, and it tells me there'd be 120 times the company is expecting to pay something around 100,000. So if they take that times 100,000, it says they're going to pay out 12 million for $100,000 policies. So you could have thought it a little differently. You could have said, oh, if there's that probability times this, tells you how many policies or how many times they're going to have to pay that out. Same with, we can take 0.0008 times 600,000, and that'll be how many policies they have to pay it on, and then take it times 500,000, and you'll get whatever that is. And you could do that for all of them, and then take 600,000 times 180 and figure out how much money they bring in, and figure out how much they actually make or lose. Okay, that's 5. 6. Fox News poll of 900 registered voters. So if they're polling registered voters, 900 of them, then the population is registered voters. Now, don't put in the 900 because that's the sample is 900. And I ask for the population. What do those 900 represent? Registered voters. Don't put in the voters that regift because no, they're polling all voters and finding out how many regift. So it should be registered voters, period. Determine the type of study. Well, it's a survey, so surveys are just observationals. We're not doing the experiment because there's no experiment because there's no control group or treatment group, and it's not a case study because case study says they go back and look at situations that have something common in them and try to find what caused whatever happened. Okay? So it's observational because it's a survey. C, determine the margin of error. Well, the margin of error is for a proportional one, a percentage one, is just 1 over the square root of the population, the size of the sample, which is 900, and that turns out to be 1 divided by square root of 900, close parenthesis, enter, is 0.0333 repeating, changing that to a percentage, which since we're dealing with percentages, is 3.3 rounded off, approximately 3.3%. Okay, so they got 19% plus or minus 3.3%. What's the smallest percentage of women that regift? It doesn't say anything about what percent of the women regift, so that's going to be hard to say. So it should be just what percentage of Americans. This didn't mention it, so I got a couple problems mixed up here. So what's the smallest percentage of Americans that regift? Well, that would be 19% minus 3.3, so that would be 15.7%, or 16% would be okay. Okay, number 7. 300 CWU students are surveyed at the CIRC. 50 opt out of the survey. What type of sample is this? This is a convenience. And if we find the sample proportions and margin of error, so we'd have the margin of error as the square root of 300, 1 over that, and we figure out what percent were for it, and we figure out that percent plus or minus. That's a nice confidence interval, but why couldn't we use that confidence interval? Why can't we be that 95% confidence based on that interval? And the reason is two. There are actually 2 reasons. First of all, this is not a random sample. And those confidence intervals are based on being a random sample. And the second one, and if you were to catch both of these on a test, if this was the test questions, you saw both of these, that'd be even bonus, but there are 50 that opted out. That's a non-participation. Bias. And there may be wording questions in the deal that have bias in them too, but those are two of the two main ones that we are for sure, from what we have, the information we have, that would be reasons to not believe, even though you calculated the confidence interval correctly and all that kind of stuff. If this is going on, that can skew the results, mess up the results. All right. Number 8, we're supposed to figure out the relative frequency. So we've got all these numbers, so I'm going to add them up. And I'm going to do it using my list just to make it a little easier. So I'm going to go to list 2 and I'm going to put in 19.18. Enter. The next one down is 17.27. 12.29, 10.06, 9.54, 9.38, 4.91, and now I've got them all in there, and I could add them up. If I go stat, calc, one variable statistics on list 2, it will add them up right here. It says the sum of the x's is 82.63. All you're doing is adding them up. And now, if I go back to the stats and edit, if you had a calculator like this, you could go up in list 3 and say, figure out these percentages by saying list 3 is equal to all the list 2 divided by 82.63 and then times 100 to make them percentages, and we get 23.2%, 20.9%, 14.9%, 12.2%, 11.5%, 11.4%, and 5.9%. You could have rounded them off to whole numbers and that would have been fine too. So that's how you do part A. Complete the table. That's the what percent is this of the total? What percent is this of the total? And all the way through. Now to make a relative frequency graph, I'll do that over here because I got a little bit more room. And so I have US, Canada, Russia, Germany, Japan, UK, and China. And so I'll make marks here so I can keep them evenly spaced or fairly evenly spaced. And then I got to put a scale on here, and the highest is 23%, so I'm going to go 5, 10, 15, 20%, 25, and I'll put 10% on here. And relative frequency. And this is the countries. And relative frequency of CO2 emissions. Okay, and then I just got to make my bars. The US one goes up to 23.2, which is about that high. Then I got to make a Canada one, which goes up to about 20.9, almost 21. Almost the same height. Then the Russian one goes up to 14.9, which is almost 15. And then the Germany one goes up to 12.2. And then the Japan one goes up to 11.5. And the UK is just about the same. And China is at 5.9, just a little over 5. 1/5. So I got my labels and my graph and my in relative frequency. And then we're going to go to how many degrees on a pie chart? Well, Russia was 14.9% of the 360 degrees on a pie chart. So I would take not 14.9 but 0.149, changing it back to decimal, taking the 14.9 divided by 100 times 360, and it would be 53.64 degrees. Number 9. 75 citizens over the age of 50 were given an anti-aging pill, and another 75 were given a placebo. It was found that the group receiving the anti-aging pill exhibited slightly less degeneration of eyesight than the placebo group. Determine the type of study and explain why. Well, of course, this is an experimental study, because they have a control and treatment groups. And B, determine what would have to be done to make the study be double-blind. First of all, those that are getting treated, control and treatment groups, don't know, the people in these groups don't know which group they're in. And so that's the one blind. And then the second blind, the people who evaluate the aging, the evaluators, don't know who actually were treated and who just got the placebos. So double blind, because the people being experimented on don't know whether they are getting experimented or not, and the people doing the evaluation of how they're aging don't know whether they were treated or not. Then the people doing the study would know, but not the people that are doing the evaluations. 10. Describe a situation where you think there is a positive correlation, so as one gets bigger, the other gets bigger, and is not causal, so the one getting bigger doesn't cause the other, but there is a relationship between them that's positive, and but it has an underlying cause. So something, a third thing, is causing one thing to grow bigger and causing the other one also to grow bigger. So it makes it look like this one's causing this one if you did the study, but something else is causing both of these. And one student came in and said, well, I like to exercise. How could I do it with that? Well, what could exercise cause? And exercise could cause a healthy body, And exercise could also it maybe improve grades because you're more alert from exercising. Or perhaps you are lose weight, but that would be a negative thing. Perhaps you are able to do you're better fit. So we can put the fitness on this side and healthy body, or you could say performance in some activity and healthy bodies. So look, you might have a study that says, oh, look at the people with healthy body are more fit, or they're more alert. And so having a healthy body makes you more alert. But what's really causing it is somebody's exercising, creating a healthy body, and making you more alert. So that's a possibility. I'm not going to write that down, but that's one possibility. Another possibility is the tilt of the earth, for example. This is one I use because I'm kind of do physics stuff. As we go from winter to summer, the sun moves is higher and higher over the northern hemisphere, and so the time of the year causes it to be longer days, and it also causes the temperature, average temperature, to go up. And so you might say, oh, longer days are causing the higher temperature, but really it's the tilt of the earth and the time of the where it is around the sun that causes the longer days and the higher temperatures. So that's an underlying cause of these two things. And you could do a lot of different things. Pick one thing and say, how does it make something get better, and how does it make something else get better? That's what an underlying cause, something that causes two other things to happen. Okay. Draw a misleading graphic, and we did several, and tell what's misleading about the graphic. Well, you can do the dollar bill thing. Draw a graphic that's misleading, and then draw it non-misleading. So if we just went that way versus if we just said, okay, here's the dollar, and it got stretched to this amount, but not stretching vertically, then this would not be misleading. This one's misleading because it got stretched and raised. So there's the dollar bill model that you could use. You could also do like the ratio of men to women, how tall they are. So you might say here's 5'5" and here's 6 foot, and you might say men are around 5'10" on average, and the average height of a woman is 5'6" or something like this, and say, oh, look how much difference there is in height. Or you could correct it by saying, okay, here's 0 and here's 5 foot, and here 5'5". If we made 0, let's just do it this way: 1 foot, 2 foot, 3 foot, 4 foot, 5 foot, 6 foot. Here's the height of the men, the same number, just a little under 6 foot, and women about over 5'5", 5'6" or so, 7 or something like that. And now the men don't look that much higher than the women. So if you start at 0 versus start at 5'5". So there's some example, and you explain a little bit about what you did in your drawing. Okay. I rolled 2 dice 20 times. So that represents 20 rolls, and I got sum of 5, no times, 2 times, 3 times, 0 times, blah, 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 all the way through there. So I can type these into my calculator and do this more quickly, but you can do them on your own. I'll do some of it manually too. So 0, let's see, let's just clear this list, make sure I got it right. 0, 2, 3, 0, 1, 2, 1, 5, 2, 3, 4, 3, 5, 1, 4, 2. There they are. If I go stat, calculate the one variable statistics on list 1, it'll tell me that the mean, it says find the mean, it's 2.375. It'll tell me the median, if I come down here, is 2. And the mode, I'll just make the list here I'm going to do a little bit of my calculator to make it easier for me. Stat, list, go to operations and sort ascending list 1, close parenthesis, and now list 1, stat, edit, list 1's in order, and we had a 0, 0, 3 1s, how many 2s? Looks like there's 3 2s, and then there's 3 3s, and then there's 2 4s, and then there's 2 5s. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 of them. And that's what I said. Oh, I repeated this experiment 16 times, so I missed something. So I better check. Oh, let's go down here and make sure I got. Oh, I got 16 here. So 2 5s, 2 4s, 1, 2, 3 3s, 3 2s, 2 1s, 2 zeros. Did I count wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What did I not write down? 2 1s, 2 zeros, 3 1s. Oh, there are 4 2s. Another 2 there. Okay, there we go. So there's 16. So to find the mode, there's 4 2s. So that's the mode. Okay. Now, Tukey 5-number summary. Well, that's the min, lower quartile, median, upper quartile, and max, or Q1, 0, 1, 2, 3, and 4. And the min is 0, the max is 5, the median we decided was 2, and we get that by, if there's 16, 1, 2, 3, 4, 5, 6, 7, 8 is on one side, and 9 is on the other side of the middle, 9 through 16, so it's halfway between 2 and 2, which is 2. Then for the lower quartile, I want to go, since there's 8 of them below, 1, 2, 3, 4, it's going to be halfway between 1 and 1, which is 1. And if we go on the other side, 2, 3, 3, 3 is 4, and then there's 4 past that, so it's halfway between 3 and 4, or 3.5. So there's, and then it says draw a box plot. So I have to make a number line. It looks like I need 0 and 1 and 2 and 3 and 4 and 5, nice, equally spaced. And I want my boxes to be at 1 to 2 and 2 to 3.5. And that's my inner quartile range too, if I needed it. That's 2.5 for the inner quartile range, just in case you need it for the test or it asks for it. And then I have a whisker that goes to 5 and a whisker that goes to 0. And if I figured out my fence, I'd take the inner quartile range, 2.5 times 1.5, inner quartile range times 1.5 is 3.75, and if I wanted to put the fences on, I would take the upper quartile times 3 plus 3.75, which is 7.25. So that's clear. Up here is the upper fence. The lower fence will be down 3.75 from 1, so that's negative 2.75. So clearly no outliers. All right. Determine the standard deviation and value where 84% of the data is expected to be below that value. So we're going to figure out the standard deviation for this. So you would have 0 minus the mean, 2.375 squared, and there's 2 of those, times 2. And then you're going to have 1 minus 2.375 squared, and times, there's 3 ones, and then 2 minus 2.375 squared, and there's how many? 0, 1, 2s. There were 4 of them. And then there was 3 minus 2.375 squared, and there was 3 of 3s, 2 of 4s, and 2 of 5s. 4 minus 2.375, and 5 minus 2.375, and these are all squared. Times these, and I can figure what that is on the calculator a little bit faster here. Oh, I did that wear off where you couldn't see it. I apologize. 0 minus the mean squared, 1 minus the mean squared, 2 minus the mean squared, 3 minus the mean, and there's 2 zeros, 3 ones, 4 2s, 3 3s, 2 4s, and 2 5s. And so now I'm going to do that on the calculator. Stat, edit. I have all my numbers in list 1. And I'm going to go do this again. Now I'm going to redo list 1. Enter. Clear. Come down, and I'm going to put in 0, 1, 2, 3, 4, and 5. And I'm going to put here how many times they happen. There was 2 zeros, 3 ones, 4 2s, 3 3s, and 2 4s, and 2 5s. And the rest of this I want to delete. Okay, so on list 3, I'm going to clear, and I'm going to make it parenthesis list 1 minus the mean, which was 2.375, close parenthesis, square that. So that's going to take each one of those in list 1 and square them. Then I'm going to multiply it by list 2, and that will be list 3. And so I've got 11.281, 5.672, 0.563, and 1.172, and 5.2813, and 13.781. So there's all of those. You add those up, and so I'm going to quit and do that. Second list, operations, math, the sum of list 3, and they come out to be 37.75. They kept all the digits in there, but so you should get something close to that. So that so far we have the sum of xi minus the mean squared, and then we added them up, so we got this number. We have to divide it by n minus 1, and since there were 16 of them, this would be 15, so I'm going to have 37.75 divided by 15, and then we're supposed to take the square root of whatever that answer is. So 37.75 divided by 15 is 2.51, and then take the square root of that answer, and I get, so this is the square root of 2.517, and this becomes 1.586 is the standard deviation. I probably did that too low. I'm having trouble staying underneath the camera. So this was the sum of the differences of them squared, multiplied by how many times they got them, divided by how many in the sample minus 1, 15. I did that division, and then I took the square root, and that's the standard deviation. And determine now, so we got the standard deviation, and then we need to find the margin of error. And I'll give you more room on the test, but I'll do it up here. So the margin of error is, for the 95% confidence interval, which is what we're working with here, is 2 times the standard deviation. So I'm going to take this times 2, and it's, well, I'll write it down here. 2 times the standard deviation divided by the square root of the size of the sample. So I took 2 times that, and I got 3.17 divided by the square root of the sample was 16. So that's square root of 16 is 4. So I got to divide this by 4, and I get 0.793. That's the margin of error. So I take the mean, which was 2.375, and I'm going to add or subtract the margin of error, which is 0.793. So 2.375 plus my answer that I have up here. Okay, and that is, so if I add it, I get the top of 3.168, or 3.17, and the bottom when I subtract it, so now I have, that's going to be, I don't have it here, so I'm going to have to go 2.375 minus 0.793, and that is 1.582. There's my 95% confidence interval, which means 19 times out of 20, that's 95%, or 95 times out of 100, the true mean of the population should be in between here. And it does turn out that the theoretical 2.22 is between those two. So it fell in there. So we'd say, okay, these dice must be fair because it gives a good sample. A recent poll of 2,500 randomly selected Washingtonians shows 49% favor stronger gun controls. Determine the 95%, well, the margin of error. For 95% confidence is 1 over the square root of 2,500, which is 0.02, I believe. 1 divided by the square root of 2,500 is 0.02, but we changed it to percent, and so it is 2%. So we have 47% plus or minus 2, the margin error of 2%. Determine the confidence interval. So we have to take 47 minus 2, which is 45%, to 47 plus 2, or 49%. We're 95% confident. Now I'm explaining. We're 95% sure that the true percent that are in favor stronger gun controls in Washington is somewhere between 45 and 49. If this was there. So somewhere between 45 and 49% of the Washingtonians favor more gun control, if this was a real poll. And that's the sample test.